Okay, so here we are, position, velocity, acceleration, part 3, and this will be the final part. The part 1 of this lesson actually took us through, let me page back here. Part 1 of this lesson actually started right here. And we talked about why the derivative of position is velocity and why the derivative of velocity is acceleration. We talked about that SVA order of derivatives. We did some example work back here. We took some examples down on these different ideas, and then we left with these last 2 pages being blank. So that's what I want to do today, is I want to fill in these final 2 pages of notes from the packet. So we're going to start with this first one. And what's really interesting about this first one is that we have to get it straight in our heads that we are looking at the graph of position. Let's read this. The graph shows the position, and that's where you got to get your brain. Position, S of t, of a particle moving along a horizontal coordinate axis. So this graph, marked S, is going to give us all of our positions. What I like to tell students is, that means if they ask me anything about which way I'm moving, that has to do with velocity. Like, I know I'm moving left when velocities are negative, and I know I'm moving right when velocities are positive. So if you look at part A, when is the particle moving, that's a velocity, left, negative. So I want to know when my velocities are negative. So we have to go back to the order of derivatives, SVA. So if I want to know stuff about velocities being negative, I've got to think derivative of position. This is position. Derivative of position is slope of the tangent line on position. So I've got to look to see where my slopes are negative. Pretty simple. If I look at this graph, my slopes are negative right in here. So I would say from 2 seconds to 4 seconds, I'm moving left. So that's what I'm going to answer. So my times would be between 2 seconds and 4 seconds. And that's because the slopes of the tangent lines on the position graph are negative. Okay, let's look at part B. When is the particle moving to the right? Moving, velocity, right, positive velocity. So I have to look at where the slopes are positive. So back up to my position graph. My slopes are positive right here between 4 and 6. So I'm going to go t between 4 and 6 seconds. Simple. Okay? Part C up here. When is the particle standing still? Standing still would be a velocity of 0. So where are the slopes? 0. Well, I see 2 instances here. My slope is 0 right here from 0 to 2 seconds, and again here from 6 to 7 seconds. So I'm going to say my particle is standing still between 0 and 2 seconds, and I'm going to give this union symbol, since I have another interval, I'm going to go 6 to 7 seconds. Now the reason I'm including the 7 and the 0 is because they're not fighting with anybody on the other side. Here we have a corner, so at 2 seconds, this guy can't claim the 2, and neither can this guy, because I'm non-differentiable. So I'm going to open the 2, open the 6, because I have corners there, but close the endpoint 0 and 7. Yeah, so that's that. Now they want me to graph the particle's velocity and speed. Okay, simple. Velocity is the derivative of position. So I must model the slopes of the tangent lines on this graph. So let's look at those slopes. It looks like, well, 2 of them are really simple. The slope here is 0, and the slope here is 0. The slope here on this segment is going to be negative something or other. I just have to count my rise and my run. So it looks like I'm coming down 4 and over 1, down 4 and over 1. So I'm going to go ahead and say that that slope is -4. And then on this guy, my slope is positive, and it looks like I'm going up 2 over 2. I'm rising 2 and running 2, so I'm going to go ahead and call that a slope of +1. So modeling this down here on velocity, I'm going to show that between 0 and 2 seconds, my slopes are 0. Between 2 and 4 seconds, my slopes are -4. Between 4 and 6 seconds, my slopes are 1. And then between 6 and 7 seconds, oh, and those should be, my marker's bleeding a little bit. These should both be open. That should be open, open. And between 6 and 7 seconds, I'm back to 0. So open here, closed on the 7, and on my 0 there. Okay? So that is going to be my graph of velocity. Now, to graph speed, all I have to do is copy over velocity and reflect the negative parts up to positive. So that's just going to take this guy and swing him up above the t-axis. So that will look like this. This will stay the same. From 2 to 4, I'm going to be up at +4 now. From 4 to 6, I'm going to still be at +1. Let's see if I can do a better job keeping those dots open here. And then from 6 to 7, I'm still at 0. So there's my graph of speed, the absolute value of velocity. Last question here, when is the particle moving the fastest? Well, what's nice is because I have my speed graph, I can see that my particle is moving fastest right here between 2 and 4 seconds, this part right here. So for t between 2 and 4 seconds, I can either read the speed graph, which I just did, or I could also look back at my original graph. My slope is the steepest between 2 and 4 seconds, so that means my velocity would be the highest between 2 and 4 seconds. So I could either just read speed right here, or I can look at steepest slopes on my S of t graph. So that's sort of how you do things when you're looking at a position graph. Now, the next one, which is our final example, you have to get your brain in a different frame again, because now we're looking at a velocity graph. Again, this is like the example we did in the last video. When the velocities, which are the y values on this graph, when they're above the x-axis, we've got rightward movement, and when we're under the x-axis, we have leftward movement. We're not looking at slopes. These are the velocities. So above the t-axis, rightward movement, below, leftward movement. So for part A, when does the particle reverse direction? Again, this is going to be when your velocity changes sign from right to left or left to right, and when you cross through and your velocity is 0. So I'm going to say when t is 1 and when t is approximately, I'm going to say about 4.2 seconds. And that's because velocity is 0 and changes sign. When velocity changes sign, you have a change in direction, right to left or left to right, up to down or down to up. Okay, letter B. When is the particle moving at a constant speed? Okay, well, let me graph my speed. So if speed is the absolute value of velocity, then all I have to do is take my velocity graph and reflect the negative parts upward. So my graph of speed will look like this. Everything will stay the same except the negative parts will reflect upward. So I would say speed is going to look like that. Okay, when is the particle moving at its greatest speed? Well, all I have to do is read my speed graph. So it looks to me like this guy right here would be the highest speed, right here. It's where the speed graph is the highest, and if I trace him down to the t-axis, that happens at 3 seconds. And last but not least, they want me to graph acceleration. Graphing acceleration given velocity is going to be that same graphing technique where I represent the slopes of this graph over here, because acceleration is derivative of velocity. So I need to find my slope of these different line segments that connect this velocity graph. So let's start the slope here from 0 to 2 seconds. Looks like I'm coming down 2 and over 1. So I'm going to give that a -2 slope. So from 0 to 2 seconds, I have a -2 slope. Then from 2 to 3 seconds, it's a little less steep. I'm coming down 1, right 1. So from 2 to 3 seconds, I've got a -1 slope. From 3 seconds to 5 seconds, I've got a positive slope. Looks like I'm coming up 5 and over 2, so we'll give that a 2.5 slope from 3 to 5. And then last but not least, from 5 to 6, I've got a 0 slope. So I'm going to come down for a 0 slope there. So that is going to be my graph of acceleration. And that concludes the position, velocity, acceleration videos. Now, the homework for tonight that's going to go with this is going to be this. Classwork/homework for section 3.4. You're going to start with this guy, the dynamite blast, which is kind of going to model the little ant problem we did on video 2. And then as you open this up, it's going to get into these graphs that we just went over. Just be sure as you're working through these that you're very aware if the original graph is position or velocity, because that's going to make all the difference in the world when you're answering your questions. Okay, thanks for watching. Bye-bye.